Welcome to lesson number 3, Trends in Atomic Radius. Our lesson objectives: describe the trend in atomic radius, explain why the trend in atomic radius exists, and compare the radius of atoms to ions in metals and nonmetals. The atomic radius is an approximation of the size of the atom. And the values for atomic radius are located on table S on the right-hand column, and our units are in picometers. So now what we're going to do is look at some of the trends that exist in terms of the atomic radius on the periodic table. When we go across any period, there is a general decrease in the atomic radius. So why does the size of the atom decrease? Well, the nuclei have greater nuclear pull. What does that mean? Well, it means that as we go across any period, there's an increasing number of protons, which means an increasing number of positive charges, which is going to pull those negative electrons in closer to the nucleus, which is going to decrease the overall size of the atom. So here's an example here looking at period 3. This example is aluminum and this one is chlorine. And you'll see the radius from table S is decreasing, going from 124 to 100 as I go across this period. Why is it decreasing? Because aluminum has only 13 protons, only 13 positive charges, and our chlorine has 17 positive charges. So there's a greater number of positive charges, greater nuclear pull, pulling in these negative electrons and the shells as well, closer to the nucleus, which decreases the overall size of the atom. Going down any group, there is a general increase in the atomic radius. And that is because as we go down any group, there's an increase in the number of energy levels or energy shells, which is indicated by the period number. So here is group 1. As we're going from lithium to sodium to potassium, you'll see the overall size gets larger because lithium has only 2 shells, sodium has 1, 2, 3 shells, and potassium has 4 shells. So more energy levels, a larger atomic radius. So here's an overall view of the trend in atomic radius. As we mentioned, the atoms decrease in size going from left to right, and then they're going to increase going down a group. And that is because, as we said, there's an increase going across a period in the amount of proton pull or nuclear pull. So the best way to remember that is period proton pull, and then going down any group, there's an increase in atomic radius due to more electron shells. So let's check your understanding. Can you describe the trend in atomic radius and explain why this trend exists? So let's focus on using table S to determine our trend. There's no need to memorize the trends that are going to decrease going across a period or increase down a group. You can use table S to your advantage. And so you can pick a row or a group and note the values of those elements. So for example, going across a period, what is the trend in atomic radius? So if you don't remember that, you can use table S to figure that out. So I can pick any period. So this example, I'm going to pick period 2. And I'm going to pick one element on the left-hand side and one on the right. I always avoid group 18 because some values are not listed for some of these trends we'll examine this unit. So I'm picking lithium and fluorine. I'm going to go to table S and look up their atomic radius. And so here is a cutout from table S, and we see that lithium's atomic radius is 130 picometers and fluorine is 60. So there's a big decrease in the atomic radius going from 130 to 60. So my trend going across a period would be then decreasing. Let's check your understanding. Can you describe the trend in atomic radius and explain why this trend exists? Now let's recall that when we look at metal atoms, these are everything left of the staircase on the periodic table, they form positive ions to become stable. So you see here, lithium is going to lose an electron to form an ion, sodium does the same thing, and so does potassium. And so they're forming positive ions by losing those electrons, and if you look at the size of the ions compared to the original atoms, the ion size is much smaller. For example, lithium atom goes from 156 to 60 picometers for the ion. Why? Well, that's because they are losing electrons, and so when they lose electrons, they're also losing that outer shell to form these cations, and so the atomic radius will decrease. What about the nonmetals? These are the elements to the right of the staircase. Well, nonmetals are going to gain electrons to form anions. And so when they gain electrons, the overall size of the atom is going to get larger. As you can see here, fluorine atom is 62 picometers. It gains its electron, and then the fluoride ion is 133 picometers. So looking at an overall view here, for our metals left of the staircase, we see that the atoms are larger than the ions because the ions have lost electrons. And for the nonmetals to the right of the staircase, you see that the ions in green are larger than the atoms because the ions have gained electrons. So let's check your understanding. Can you compare the radius of atoms to ions in metals and nonmetals? At this point, you should be able to describe the trend in atomic radius, explain why the trend in this atomic radius exists, and compare the radius of atoms to ions in metals and nonmetals.